Hello and welcome to this free training video. My name's Steve Bungard and I've been a successful embedded systems developer for over 30 years now, and I am also an online trainer and mentor in that subject. So in this video I'm going to be sharing with you everything I know about the CAN and CAN-FD communications protocols. Let's get stuck in, shall we? Okay, we are of course talking about the CAN-bus communications protocol, not a bus made out of tin cans. Apologies for my poor sense of humour. CAN-bus is a network that communicates without the requirement for there being a master on the network. So a lot of communications protocols, there needs to be a master or a controller that sends out a request message to a particular node on the network, and that node will respond with a message. CAN-bus is different like that in that all the nodes on the network exist all at once, there's no master, and every node broadcasts a message to every other node on the network. Every other node on the network can decide what they want to do with that information. Every message that is transmitted on the network, which consists of a single twisted pair. So there's one twisted pair cable that everything is connected to, all the nodes on the network are connected to, and it has a terminating resistor at each end. So each of these messages that are transmitted out onto the network and broadcast to everything that's on the network also have a prioritization and an acknowledgement mechanism built into them. So we will get into this in a bit more detail in subsequent slides and find out what's going on there. The speed at which the network is communicating at is measured in bits per second, and everything on the network needs to be configured to the same bits per second as everything else, otherwise there'll be communications issues. There's theoretically no limit to how many nodes can be on a network, but practically speaking, it's typically 64 nodes, probably less. It depends on the quality and capacitance of the wiring of the network and also the loads that the nodes put on the network. Typical cable lengths are about 50 meters. There are more details on this online, and the higher speed you go in bits per second, the more that network cable length comes down. So each message on a CAN-bus network consists of a message frame. So a message frame consists of several segments. So this is essentially bytes that are transmitted out, bits and bytes that are transmitted out on the network, but every frame consists of certain segments that are always present, and that's how everything on the network knows how to interpret the information that's being put on the network. So there's always a start of frame bit, which is a single low bit. You can see it here in this diagram, which is the start of frame. After that you have an arbitration field shown in green here, and we'll talk more about the arbitration later. This is a prioritization section of the message where the highest priority message can essentially win control of the network. After that you have a control field here shown in yellow, which specifies what's coming next in the message, how much data there is, that kind of thing. And obviously next here shown in red we've got the data field. Now with classic CAN, like we're talking about here, you can have up to 8 data bytes in the data segment. So from 1 to 8 data bytes can be in the data field. Incidentally, you can also have 0 bytes in there if you are sending what's called a remote frame, and that's a request for data from another device. After the data there is a CRC field. So this is the checksum for all the bytes that have come previously, and that allows other devices on the network to check that the data they've got so far is correct. After the checksum we have an acknowledgement field, an ACK field, and we will get more into this later. The acknowledgement field essentially allows any other device on the network to signal whether they have or have not received that message correctly with a valid checksum. So the acknowledge field is quite important. It tells the node that's transmitting the message whether its message has been successfully received by any or all of the other nodes on the network, or if any of them, even an individual one, has failed to receive that particular message. After the acknowledge field, there is an end of frame bits, and finally an interframe, like quiet period, if you like, 3 bits worth of nothing has to happen on the network at that point. So we're going to start getting into the arbitration field and how these bits work on the network. One of the differences with CANbus is whenever you're transmitting a bit, you are also reading back what the state of that bit is. So CANbus data lines are naturally in a high state, and any node on the network can take it to a low state. And these are referred to as dominant and recessive bits. So there's a readback bit by bit while you're writing data to the network. That's quite important to understand. So while you're writing bits and bytes to the network, if you want to write a 1, that's a recessive bit. So you essentially leave the network alone, you don't pull it low. And if you want to communicate a 0, you pull the network low. Now what's important to understand here is any node on the network can pull the lines low. It's only if nobody's objecting to you outputting a 1 that you can output a 1. If any other node wants to object to the 1 that you're putting on the network, they can pull it low and a 0 will be output on the network. And your microprocessor peripheral will be reading back what's actually been put on the network. So it can write a 1 to the network and it looks on the network to see if a 1 has been successful. If it hasn't, that means another node on the network has said, no, I want a 0 here. And it's a way of communicating back to the transmitting node that what it's transmitting has been unsuccessful. So essentially, with the arbitration segment of the message, the first part of the message that comes out, all the nodes on the network will transmit a message identifier. And this is the arbitration phase of the arbitration segment of the message. So all the nodes will start outputting a message ID. And the idea here is that the highest priority message will win control of the network and continue to be allowed to output its data. So this happens whereby the ID, the lowest number ID of the message, is the one that wins the arbitration. So if you imagine that all the nodes start outputting in their ID, and any that are outputting 0 agree and they can continue, any that's outputting a bit 1 of their ID value that gets overridden by a 0 has to stop transmitting. So eventually the node with the lowest ID message to send is the only one that's allowed to continue transmitting its message. And this is how the prioritization works on the network. So the message ID with the lowest value wins the arbitration phase, where they can all override and they can all set that bit to a 0. So the lowest value will always win that and be allowed to continue with the rest of its message for that frame. Any that lose the arbitration phase, i.e. they have a higher value ID in their message, have less important information to transmit, will stop transmitting in this frame, and then they'll wait to transmit in the next frame. And during the next frame, the arbitration again will help work out which message is the next most important message to put on the network. And this carries on until all the messages of different priorities have been transmitted onto the network. One problem with this is if you have a lot of high priority messages going on the network, they can lock out lower priority messages. So your network configuration is important to make sure that you don't lock out the lower priority messages. Okay, we've talked about the arbitration segment of the frame here and how all the nodes will output their message ID throughout here, and only the node that wins this arbitration will be allowed to continue with the rest of its message. So we've covered the fact that we've got the data frame here, and that can be whatever information it is that the node is having to transfer. So now we're going to have a look at the CRC and the acknowledge parts of the message. After the data segment has been transmitted, we have the CRC, the cyclic redundancy check, and all the nodes on the network will check that the checksum adds up, that we have valid data so far. So after the CRC field has been transmitted, there's an acknowledge field, and this allows all nodes receiving the message to indicate that they have received the message correctly. Or alternatively, if there's been a communications error, noise or whatever, any node can indicate that it didn't receive the message okay, and therefore trigger a resend of the message. This ACK field and its bits allows indication of whether any node received the message okay, meaning it was transmitted okay and the receiving node has an issue, or if all nodes didn't receive it properly, in which case it's likely to be a transmission error. Errors like this are counted, and eventually if one node on the network is having continual problems with either transmission or reception, it will remove itself from the network communications to allow the rest of the network to continue without errors. Okay, here we're going to talk about how fast the bits are being transmitted on the network. And the bits that are transmitted in CANbus, unlike a number of other communications protocols, are actually broke down into bit time segmentation. So where we transmit a bit onto the network and we also read back the value of that bit on the network to see if any other nodes on the network are overriding it with the dominant bit, we have to allow for the propagation of our output to get out onto the network and to be read back. So where we've got bits per second, we also break down each of those individual bits into segments. So that's what's commonly known as bit time segmentation, and it also defines the network speed of how many bits are output per second. So for example, typically you'll be running a peripheral, a CANbus peripheral on a microprocessor with a peripheral clock speed of 80 megahertz. And this is partly so that it can be broken down into integer numbers for how many clock cycles each proportion of a bit takes. So with an 80 megahertz CAN peripheral clock, you would set your bit segment times for a 1 megahertz bit rate to be a total of 80 clock cycles. So you'd have to specify in your microprocessor how many cycles you want the propagation delay to be, segment 1, and also how much variation there can be on keeping synchronized with the message that's coming in. So if you set your segments to 63 and 16 for segments 1 and 2, obviously the clock cycle 0 is a clock cycle as well, so if you add those all up, you get 80 clock cycles per bit. And this includes this is basically defining how the peripheral will transmit a bit onto the network, and when, while that bit is being transmitted, when it will read back what signal is actually on the network. So for these settings that we've shown here, we'd get a bit rate of 1 megabits per second, or 1 microsecond per bit. And that 1 microsecond would be divided down into different segments where it would be transmitting and when it would read back what it's seeing on the network. Obviously, by now it's probably apparent that the timing of individual bits on the network is hugely important, and all the nodes on the network will be looking at the bits that are coming in from the communications on the network and working out whether it's a dominant or a recessive bit, a 1 or a 0. For that reason, it's not possible with CANbus to transmit more than 5 bits of the same value. If you imagine on the network, if you transmit 5 bits of 0, the line will be low for 5 bit cycles. And before long, if you do 6, 7, 8 bits, different nodes on the network will start to get slightly out of alignment as to where the edges of those bits are. For that reason, CANbus includes bit stuffing. So if you need to transmit more than 5 bits of the same value in a row, it will automatically stuff an extra bit of the opposite value into the message. And all the nodes on the network follow this rule, so they can automatically remove the stuff bits that are coming in to help keeping all the nodes on the network synchronized. So stuff bits are added to help everyone on the network keep synchronized with where the bit edges are. And they all know to follow the rule that if 5 bits come in of the same value, there's definitely going to be a stuff bit next. So the example here shows a 29-bit message that is expanded to 36 bits to include the stuff bits to help everyone keep synchronized with the messages that are going on. Okay, let's have a quick recap. Classic CAN runs at up to 1 megabits per second. There is no network master, so every message is broadcast onto the network, and all the nodes have a choice to absorb that information, use it and do something with it, or ignore it. Messages are prioritized through an arbitration field, so every node on the network can start transmitting at the same time, and whichever one has the lowest value message ID wins control of the network and can carry on broadcasting its message because it has the highest priority. All the messages are checksummed, so you can be confident that that message is valid and it's actively acknowledged by all recipients on the network. So you can tell whether you've transmitted it to everyone successfully, if one of the nodes on the network or more have had an issue receiving it, or if all the nodes on the network fail to receive your message, in which case you're transmitting it incorrectly. Any node on the network that is persistently causing communications errors will eventually remove itself from the network. Next, we're going to have a couple of minutes talking about CAN-FD, the flexible data expansion or extension of CANbus. Okay, now we've covered the basics of classic CANbus, we're going to talk about the CAN-FD extension. CAN-FD extends the functionality of classic CANbus while maintaining compatibility. The FD stands for flexible data and allows CAN-FD to transmit messages with a payload of up to 64 bytes instead of the limit of 8 bytes you're restricted to with classic CAN. As well as flexible data size, it also introduces bit rate switching, BRS, to allow for flexible data speed. What that means is the data field, the data segment part of the frame, can be changed to a higher bitrate speed of up to 8 megabits, while the start and end fields of the frame remain at the lower classic CAN bitrate speed, typically limited to 1 megabits per second. CAN-FD and classic CANbus messages can be present on a network. However, all the devices would need to be CAN-FD compliant for the network to operate correctly, as they'd all need to acknowledge the reception of the message. CAN-FD can operate on an existing classic CANbus network, hardware and wiring. However, the transceivers used for CAN-FD must be CAN-FD compliant, not a classic only CANbus transceiver. How this is done is with a little bit of frame magic. So essentially, in the control segment of the frame, there is a bit that says whether the bitrate switching is used or not. All the nodes on the network would need to be configured to the same basic classic CAN bitrate and the higher bitrate switching bits per second. So everyone needs to know how much the bitrate is going to switch when we go to the data payload part of the message. So there's an example of a classic CANbus 2.0 message, 8 bytes payload at 500 kilobits per second. And you can see in there that all the bits that are being transmitted in the arbitration phase are the same speed that are being transmitted in the data payload segment of the frame. Underneath that, you can see a CAN-FD message which has 64 data bytes with the data segment being transmitted at 2 megabits per second. So the start of the message, the arbitration phase where the priority is decided, is still transmitted at the standard 500 kilobits per second as the first message. However, the data segment payload and the CRC is transmitted at 2 megabits per second. So you can see here that you can transmit 64 bytes of data with CAN-FD in not much longer than you can transmit 8 bytes of data with classic CAN. This is only showing 4 times the speed of the data segment. You can go up to 8 times the speed, so you can transmit the arbitration at 1 meg and the data segment at 8 megabits per second. However, you do need to be aware that the faster bit rates you use means the higher quality CANbus cable you need to be using, and also the maximum cable length you can have on the network also reduces significantly the higher in bit rate you go to. So next, let's have a look at how you would configure CAN-FD in a microprocessor. So here I am using an STM32H7 microprocessor which has a CAN-FD compliant peripheral, and we are going to have a quick look through the settings on that in a minute. And what we're going to be looking at is the arbitration rate, the classic CAN rate, bit rate that we're going to be using on the network, as well as the data segment rate, so the higher rate that we're going to be using for the CAN-FD messages. We're going to be looking at bit rate adjustment, which is called in the settings the nominal sync jump width, and this is how this node is going to remain synchronized with the messages that are coming out on the network. And again, that's in the bit time segmentation. And all of this adds up to the propagation delay compensation. So the delay in how much time it takes for a transmit of a bit to get out on the network before you can read that back on the RX of the peripheral to make sure that your output of a recessive bit has been successful and it hasn't been dominated by another node on the network. So here we have all the settings that we have in the STM32H7 for CAN-FD messages. This is, like I said, an STM32H7, and we've configured an 80 megahertz CANbus peripheral clock. So that's the input clock to the CANbus peripheral. It's typically made 80 megahertz because that divides down to 8 megahertz, 4 megahertz, to all the way down to 1, and below that with integer divisions. So that's quite important when we start to look at the settings. So let's take our way through these settings and we will cover all these points as we go through it. Frame format at the top here, we have FD mode, so CAN-FD mode with bitrate switching. This can be set to FD mode without bitrate switching or classic CAN mode. Mode, we've got normal mode. You can configure this peripheral to enter into a test mode or loopback mode so that you can test what you're doing without other nodes on the network. Of course, because of the acknowledge segment of the frame, if you try and communicate on a network with no other nodes on it, then there'll be no other nodes to acknowledge the reception of your message, so every message you try and transmit will fail. So you can change the mode here to make it operate in a loopback mode so that you don't need other nodes to work. Auto retransmission we've got enabled here, so if the acknowledged field fails and we have been unable to transmit our message on the network, it will automatically try again. And of course, with the error counting, if it gets to the point where we're constantly causing errors, the peripheral will automatically stop communicating on the network. Here we've got transmit pause and protocol exception disabled. It's not things I've gotten into in this short presentation. And we have nominal sync jump width. Now this is set to 15, and I'm going to jump down to the bottom of the settings here, because the nominal sync jump width, it has to be set to less than the nominal time segment 2 of the bit timing parameters. So if you look all the way down at the bottom of the settings here, we've got bit timing parameters, and this is for the nominal segment time, bit time, which we've got set here to 1 bits per second. Apologies for that error. So under the bit timing parameters, we've got a nominal prescaler of 1. And what that's saying is we're going to take our 80 megahertz CANbus peripheral clock, and we're only going to divide that by 1, so we've got an 80 megahertz clock for our peripheral. This gives us a nominal time quantum of 12.5 nanoseconds. So that's how many clock cycles, one clock cycle is 12.5 nanoseconds. If we want a nominal segment bit time of 1 megabits per second, we're going to need to have 80 clock cycles to equate to 1 microsecond. So here we set the nominal time segment 1 to be 63 clock cycles and the nominal time segment 2 to be 16 clock cycles. Obviously the 0 clock cycle is also a clock cycle, so if you add all those up, you get a nominal bit time for 1 bit of 1000 nanoseconds or 1 microsecond. So that gives us our 1 megabit per second nominal segment time. The amount of time it's allowed to adjust the synchronization of the bit timing is the nominal sync jump width we were talking about earlier, which is set to 15 clock cycles. Next in the settings here we have the data segment settings, and again we're using a prescaler of 1, nominal jump width of 3, and our data time segments are 5 and 4. With the clock cycle of 0, that gives us 10 cycles at 80 megahertz, which means our data segment is going to be running at 8 megahertz. So we're going to be running our frames on our network with a 1 megahertz nominal bit time segment, which is the classic CAN part of the message, and our data segment we're going to be running at 8 megabits per second. So that's the settings we've got there under the data section. Next we get into other parts of the peripheral that are automated for us. We've got a RAM offset, number of filters. Filters are an automated way of excluding receiving messages that we're not interested in. So essentially with the filters you can specify a range or specific message IDs that you're interested in, and the peripheral will automatically ignore messages with IDs that you've not specified that you've wanted. As we've got here shown here, we're not ignoring any messages, we haven't got any filtering, so we're going to be receiving all the messages in our micro. The peripheral includes a FIFO, a first in, first out message buffer, an RX FIFO, so this is messages we're receiving, and I've set this to the maximum of 64, so we can receive 64 messages automatically in the peripheral that we can process in our microprocessor as and when we want to. And each of those element sizes, so each of the RX FIFO elements has a size for the data buffer, and I've specified here the maximum of 64 bytes. So we can receive 64 messages with 64 bytes each. Sorry, I've clicked my mouse again. Apologies for that. So we can receive 64 messages with 64 bytes each in the peripheral automatically, and then we can process those in a microprocessor. And I've left the other, we have 2 of these buffers, and RX buffers, and I've left the other one empty. And we also have some transmit buffers and FIFO. So I've configured the transmit first in, first out queue to have up to 5 messages that we can queue up for transmission, and they are 64 bytes each. Lastly, here we have a clock calibration that is disabled. That will transmit occasional messages on the network so that other devices on the network can all communicate with each other and synchronize their clocks for better performance. So that's been a whirlwind tour through CANbus and CAN-FD and all the settings that are involved in that. Obviously, if you're configuring classic CAN, you won't have a subset of these settings about the data times and all that kind of things to worry about. But yeah, that's everything I know about CANbus and CAN-FD. Thank you very much for taking the time to watch this training.